Hi, everyone. Welcome to Ambient Scientific's webinar on optimizing AI models for edge devices. How's everyone doing? While we wait for a few minutes for most of the people to join, let's test out some of the features in the webinar. Let's make sure that everyone can access all the features. So I think the first thing people will see is the chat option. So why don't we have everyone tell us, where you're joining from, what city, what country, so we'll get a sense of where our audience is from. Okay, I'm seeing Pune in the chat, Hyderabad, Singapore. Oh, okay. Delhi, Pune, a lot of people from India joining in. Awesome. All right, let me go ahead and start sharing my screen. So I hope everyone can see my screen. So while we wait for our primary speaker to come into the webinar, I just want to give everyone here who's maybe not familiar with Ambient Scientific or what we do, a little bit of a quick introduction about who we are, what we do, and then we'll slowly bring in our speaker and he'll get started on the topic of the webinar. So today we're going to talk about smarter models on linear hardware, and our speaker is going to be Madanjeet Singh. But before that, just to tell you a little bit about Ambient Scientific, who we are. So we're a fabless semiconductor company. We're building high performance, extremely low power programmable AI processors. As a company, we're headquartered in Silicon Valley, California, but we have an office in Bangalore, India as well. And our mission as a company is to create the world's next leading AI compute platform by bringing energy aware intelligence into every device. So we believe that AI should exist from the smallest of devices, like your hearing aids, all the way to large cloud server racks and so on. And why we think this mission is very important and critical for us is if you look at AI compute today, whether it's at the edge or in the cloud domain, there's some fundamental problems with how AI is currently computed. It's that GPUs, for example, which are used in the cloud server racks, were never really designed for AI computing. And as a result, they're not the most efficient devices for running AI compute. They consume an enormous amount of power, which results to a lot of overheating and requires cooling overhead in the data centers. And for edge applications, they're far too large, far too expensive. Again, consume so much power that batteries cannot power GPUs effectively. So essentially, as a company, we realized that AI compute needs a new architecture to be truly effective, to be able to disperse its benefits all the way from the edge to the cloud. And in order to solve this problem, as a company, we built completely new compute architecture from the ground up. So this means, a reinvention all the way from the circuit level to the instruction set level to the software stack level. Our compute architecture, which is entirely novel, is called DGAN. It's a play on two words, digital and analog, because our compute architecture is actually hybrid analog digital in-memory compute. Some core elements of this architecture are in-memory compute. So this means that the compute actually happens very close to the memory, because in AI compute, a lot of the power is wasted in shuttling the data back and forth between compute and memory. The max or the multiply accumulates. The fundamental operations behind AI computing neural networks happen in the analog domain, which by definition of physics is a lot more power efficient than digital max can be. And several other SoC level IPs that we've invented, whether those are in event-driven activations, sensor fusion on chip rather than being done in software, and a completely new software stack to eliminate users having to relearn or redevelop their AI workflows that they're already used to. With this architecture, um, we're able to create an entire roadmap of processors for AI compute, all the way from small edge devices, small battery power devices, to cloud supercomputers, drones, robotics, small edge servers, enterprise computing, and so on. And our first product from this roadmap is actually already out. It's called GPX10. It's targeted for battery-powered edge AI computing. And it actually opens up a whole new category in the market that we like to call coin cell AI. It's powerful enough to power AI algorithms right at the edge. So no need for offloading any compute to the cloud. Everything happens at the chip level itself. It's absolutely tiny in form factor, so smaller than your fingernail, can fit into devices like hearing aids that disappear into your ears, completely energy aware, so hundreds to thousands of times less power consumption than your typical processors like microcontrollers, GPUs, so on, and very, very flexible, very programmable processor as well. So it can adapt completely to the evolving landscape of applications and whatever you as a developer or user would want to use this for. So this was a very quick overview about what we do as a company, what our products are, and what's the innovation and the breakthrough technology that we've invented. Now, before I pass this over to um, our speaker for the day, I just want to give you guys a couple of reasons to stick around till the end. The first reason is that at the end, whoever's still listening to us, we'll be giving away one of our development kits for free to one random lucky winner. And at the same time, while our speaker Madanjeet will go over all the theory for how to optimize AI models, he will also show you a live walkthrough demo, and all the materials ranging from this presentation to the actual code scripts for the compression workflow he will be showing will also be downloadable. So if you guys just check your resources section, you'll see that there are a couple of documents there that you can download, look at in the meantime, and there's quite a few links there as well. And now I will pass this over to our speaker for the day, Madanjeet. So just allow me a minute to bring him in. All right, there we go. So we have Mr. Madanjeet Singh here. He can introduce himself, start sharing his screen, and we can go through the presentation. And we want to keep this more of an interactive session as well. So if any of you have any questions, please feel free to put them in the chat. There's an option for you to add questions. Other people can upvote those questions as well. So when we see that some questions are getting more upvotes, we'll definitely take a pause and answer those for you.
Thanks, Sahas, and good morning, good afternoon, or good evening to everyone joining us worldwide. I'm Madanjeet, Vice President at Ambient Scientific, where I lead software applications, data science, and AI compiler development. Ambient Scientific is a fabless semiconductor company focused on building next-generation compute platform for intelligent AI and micro AI devices. It's my pleasure to welcome you all in today's webinar of optimizing AI models for edge and micro edge devices. This session will explore how to compress and optimize deep learning models, reducing from megabytes to kilobytes without significantly sacrificing accuracy, enabling deployment on edge or even micro edge platforms. We'll start with an overview of edge AI, discussing resource constraints and the motivation behind model optimization. Then we'll dive into the practical techniques such as, these are very common techniques like pruning, clustering, knowledge distillation, QAT, quantized aware training, or post-training quantization. In the live demo, I'll show you how a base neural network model can be progressively compressed and quantized step by step until it's ready to efficiently deploy on the resource constraints hardware. By the end of the webinar, I'll have a clear understanding of the methods and workflows that transforms an AI model from cloud to edge, and hopefully some inspiration to build your own ultra efficient AI solutions. So let's get started. So before we dive in, let's do a quick fact check or pulse check. How many of you have hands-on experience with edge AI? This will help us understand the mix of experts and learners in the room.
And I've launched a poll just now, so all of you can access that poll. So let's see, we have some responses coming in very quickly. Okay, so we see that there's a good mix of folks in the audience here. While most folks are just getting started with Edge AI, there's some who are building the momentum around 20-25% of folks. And then we see some people who are not directly engaged in edge AI either, but curious to learn as well. So awesome, very good.
Yes, that's
So I think
correct.
we can get started, Madanji.
That's correct. So this is nice. We've got a good mix. Thanks for sharing. No matter where you are on your HA journey, be it a beginner or experts, the next few sections will give you useful takeaways you can apply in your projects. Okay, with that, I'm moving to the slides. So, can I have to remove this slide. Okay. All one is done. Then moving on to cloud. So let's say cloud compute. It's like cloud compute is called a centralized processing, where the endpoint, like where the devices are connected, like sensors, camera, or user devices, is responsible for capturing the raw data and transmitting it directly to the edge or cloud computers. Edge computer role is to act as a relay point, receiving the data input from the endpoint and forwarding to the cloud. The cloud computer handles the entire AI processor workloads, and the data flow in this case is going to be high volume as all data must be transmitted from endpoint to cloud. The concern for this is its high latency, data privacy, connectivity, and cost. To overcome this, the edge compute comes into picture. Edge compute is like decentralization process where the endpoint performs the AI compute at endpoint itself. It processes the raw data locally and determines the results. The edge compute may facilitate the connections or perform further localized processing. Cloud compute, what it does is the cloud compute receives input only with its necessary results, like processed output. You can send it for analytics or for dashboard creation and so on and so forth. In this case, the data flow volume is going to be very less, and it's transmitted only when it's essentials. Like cloud concerns address are the low latency, the data in local, not sorry, data is completely local, it's going to be reliable and very low cost. Moving on to next slide. Okay, so HCI application, it's like, it's can enhance almost every aspects of day life or day-to-day life which we go through. Here are the few examples. Like smart helmet, you could see that. It improves rider safety with 360-degree awareness, collision avoidance, and enhanced visibility. Industrial machine monitoring, like analyzing vibration and temperature data in real time to predict fault and prevent downtime. Driver drowsiness or driver monitoring system, like monitoring the driver's face and issue instant micro sleep or distraction alerts. Uh, you could see that smart collars, like when you have it does enable real-time pet tracking, health monitoring, and behavioral analysis with instant escape notifications. So battery powered edge and micro edge devices. Edge devices like single board computers, we call it GPUs, like NVIDIA Jetson, TPUs, Raspberry Pi, and similar platform. These devices have power budgets in watts. It's not in milliwatts, in watts. And the model size which can run on those edge devices are up megabytes in size. Micro edge devices are like custom AI processor, like we have GPX10 or this 5 best microcontrollers which are available in the market. The power budgets for this are going to be in microwatts and milliwatts, and the AI model size are typically going to be in the kilobytes. Key resources constraints for edge devices, edge or micro edge devices. First is memory. It's going to have limited memory, like in KBs. In some cases, you see 2 MB or 4 MB or 8 MB, but mostly it's going to be, let's say, 256 kilobyte or 128 kilobyte or so on and so forth. So for that, to make it run a model, you have to make your model smaller enough by compressing and quantizing it. The latency is second one, where now fast and real time response is required. For that, you have to run processing or AI model has to run locally. Thermal and heat processing, like fan devices can overheat easily in edge devices. So what you have to do is keep your AI model light to avoid heat and performance drop. The compute like CPU and processing, or maybe in some cases it's going to be custom CPUs. So low processing power and slow clock speed that comes into picture. So what you have to do is you have to use efficient code or optimize code in such a way that it's working properly even with the slower clock speed. Battery is another problem because on Asian micros devices, even in fact, milliwatt matters. So reduced active time to save battery. In most of the cases on edge devices, what we do generally is we do duty cycle process. So every 10 seconds or every 10 minutes or every 1 hour, we'll do the duty cycle, we'll do the inference and then we'll go for sleep. Okay, that's a process. And connectivity and bandwidth, like the internet may be slow or unreliable. What you have to do is do most of the things offline and minimize the data transfer.
All right, so it's
Yeah.
time for the next poll, which I will just
Another batch.
launch now. So we're curious to know if any of you have tried Edge AI at deployment before. What do you consider the toughest challenge, or what would you imagine as the toughest challenge? And while the audience is answering that for us, Madan sir, some people are pointing out that the slides are visible only halfway. So if you don't mind zooming out a little bit on your
Okay,
application at the top.
let me do that.
Just hit the minus magnifying glass button, and I think that should solve the problem.
Okay, let me do that. I was just trying to get it.
Yeah, right there, right there. You see the minus option with the to zoom out,
For, for, for
magnify.
me, it's for me, I'm not able to see that button. Somehow this overlap is coming and I'm not able to maximize it.
There we go. I think it's a little better now. If you can just scroll down,
This is
we'll be
better.
good.
It's better.
Yeah.
Okay, thank you.
So it's interesting. We're seeing the answers to the polls where two options are neck and neck. So most people think that the biggest challenge for AGI deployment for them is the on-device model optimization. So actually how to optimize the models when they're deployed on hardware. And this might have something to do with the hardware specific architecture with so many different chips out there. And the second option that's very popular is the hardware software integration gap. And these are actually both great answers because the following section will exactly address how to solve these problems.
True. And as far as I have seen, there is no single biggest challenge. It's always depends on your application or your use case. That's why optimization has to be customized. What matters for a drone might not matter for wearable devices. So that's what it has to be driven based on use cases you are thinking of. And then you can optimize or quantize level where it can be deployed on best devices. Right.
Okay, awesome. So I think you can move on now.
Yeah. So moving on to next. Okay. This is popping up again and again. So this is fine.
Scroll down a little more. Yep, I think that's better. Yeah.
So over the year, we have seen AI models have become larger and more data hungry, right? So if it's larger, then deploying it to real life scenarios becoming harder. So while the cloud offers scales, it also adds latency, privacy risk, and power overheads. So Edge AI solved this by bringing intelligence closer to the data from where the data is getting generated. From wearable and smart cameras to industrial sensors, on-device AI enables real-time decisions, lower bandwidth usage, stronger privacy, and better energy efficiency. The optimization goal. So the AI optimization triangle, what happens is, when you're deploying an AI on the edge devices, it involves balancing three key factors: the accuracy, model size, and latency. Improving one often impacts others. So the goal is to build a model that is accurate enough, small enough, and fast enough for the target hardware, like reducing latency. If you reduce latency, it enables faster real-time response. Reducing model size minimizes memory and storage footprint. Maintaining accuracy, like preserving reliable predictive performances. As a data science, most of us, we are data science. So as a data scientist, our job is to strike a balance between accuracy of the model should be accurate, yet small and fast enough to run efficiently on the target hardware. And in this case, the target hardwares are going to be memory constraints devices like the RAM is of 128 kilobyte or 256 kilobyte and so on and so forth. So approaches to model optimization. Most used techniques in the industry and supported by AI frameworks are, the first one is model pruning. So pruning could be at two stages. One is structured pruning, second one is unstructured pruning. Weight clustering is the second one. Quantization, again, quantization also are of two parts. One of them can be adopted based on your use case. First one is quantize aware training, where at the beginning itself, you are inducting the quantization. And post-training quantization is like, when the model is generated, then
Can
you
you
can
scroll
time
down
it.
a little more? Sorry, there's requests coming in. Yes, they cannot see. Yes, yep,
Oh,
that's
sorry.
fine now.
Sorry. Okay. So the post-training quantization is like, when the model is built, you can take some of the samples and calibrate your model for model to understand what kind of input you're going to get. Based on that, it will create the coordinates. Knowledge distillation, again, it's like, small uh, training of small student model using a larger teacher model. Low rank factorization, it's a mathematics function. Neural architecture search, it's a NAS, which is very common. And it's actually creates a compact architecture for your use case. Hardware aware training, again, like based on hardware, you can optimize your training process. Okay, let's see what each of them does. Okay, so first technique is pruning. So pruning could be the two steps. One is when you understand the architecture well. Let's say you have got a model which is created by someone. When you understand the architecture, you can prune your model in such a way that because you can reduce the size. The size reduction can happen by using uh, two things. One is going to be your filters or kernels, and second one is the depth of the network. That's going to be structured pruning. And then unstructured pruning is like, making some of the weights at zero, still without impacting the accuracy of the model. Which is again, you have to fine tune once you do that. Okay. Second technique. So there are 5 techniques I have listed here, which you are going to experience live with the demo I have. So weights clustering. So what happens is imagine rounding many similar weights to a small set of representative values. That leads compression algorithm packs the weight efficiently while retaining the accuracy of the model. This is very common techniques. The weight clustering is like you can do for almost all the applications or use cases you're using in your AI workload. Third technique, quantization, we discussed already. So quantization could be of two different type of quantization. Post-training quantization always comes into picture when someone has built the model, and they want to quantize it from FP32 to let's int 8. And second one is quantize aware training, where your model will go through the complete data set we have used for training purpose. So this the difference is like quantize aware training will go through the complete data set which we have used for training, and post-training quantization will actually take a subset of data and you have to just calibrate it. Definitely the accuracy will impact. Quantize aware training will give more accurate result than post-training quantization, but we haven't seen much of a difference into it. Okay, it's very less difference I have seen that. Okay. Third pole. So, sirs, you want to take or which
Yes,
optimization?
so
That, please.
yeah, so now we're curious to know if any of you have any experience with one of the techniques that we just talked about. how where you might have used it and which you think might be most useful for you. And if you have any questions about whatever we've talked about so far, please feel free to put those questions in the Q&A section, and we'll answer them either as we go through it or at the end.
Sure.
So we see that most people have some experience with quantization. So there's a split. Half of the audience has not used any optimization techniques yet. So this is a good opportunity because we'll share the full model compression workflow, the script, the code with you at the end. And we see that most people have experience with quantization, which doesn't surprise us because that's usually built into a lot of the TensorFlow, PyTorch module. So it's fairly well known compared to some of the other methods.
So that's great, because today's session will walk you through all these techniques step by step, from simple to advanced, and shows how that connects to a real life compression and quantization pipeline. So that pipeline will have in a demo. We'll see that how the pipeline is working from start to end. And quantizing a model which is built as a base model in megabyte to the final model which you're going to get is in kilobytes, without impacting or hurting the accuracy which you can expect from that model.
Okay, I think we can move on now.
Yes. So additional optimization technique we have already discussed. Knowledge distillation, like smart student mimicking a large teacher. Low rank factorization, it's called a concept called singular value decomposition. It's a low ranking factor. What happens in this, generally used for model compression and dimensionality reductions. NAS, again, standard can go and search that. These are used for standard efficient model development, like one of them is a mobile net or efficient net and so on and so forth. Compiler and graph optimization. If someone has worked on graph, you can understand. Before developing a full-fledged compiler, you have to first understand the operators which are coming in, fuse the operators in a sequence so that you'll get optimal result, removing dead nodes and quantized graphs. Okay. This is coming again and again. Okay. Okay, coming to optimization pipeline. Okay. So many engineers, what they do is start quantization too early. Then what happens is you lock your numeric values, and later on, if you want to do something else, you'll not be able to achieve the result. So the thumb rule we follow is prune first, cluster next, and quantize last, if you're using in this sequence. Okay. The recommended orders, the best practices which are recommended, like, no, you create a base model, which is going to be your full precision model of FP32, trained for high accuracy before compression. Second one is going to be structured pruning. We discussed that if you understand the model architecture, you can remove some of the nodes, you can remove, or you can reduce the filter sizes, you can remove or reduce the neurons, and ensure that the model is still performing the way it was performing with the base model. Second, pruning is like, again, you're reducing or ensuring the weights, 50% or 30% or 40% weights are marked at 0. Because if you see the weights in any neural network, the weights are going to be between 0 and 1. With 30% or 40% weights will be close to 0, like 0.001, minus 0.002, something like that. So that kind of pruning you can do to reduce the number of weights. Clustering, sorry, clustering is like weight sharing. We discussed already. So grouping weights into a few shared centroids. It's like k-mean. You decide the k-mean like 8, 16, or 32, and based on centroid, you can achieve the pruning or reducing the number of weights in your model. Fourth one, like QAT or PTQ. QAT is quantized during training to recover accuracy. So it's a process where you're training a model. Once, let's say, using Keras or TensorFlow, you have created TF or .h55. Then from there you can quantize it, and then later on you can convert it to TF, right, to get the full feature of it. Okay. Fifth stage is going to be TF light conversion, because until unless you do conversion to TF light, you'll not be able to see the actual result, what you have done in pruning, clustering, and QAT. Because whatever is done, still your weights will hold 32-bit values. So to convert that, you have to convert the model which you have into TF-lite. Then only you can get it. So question comes in like, why this suboptimal sequence comes into picture? Because when you do a base, think of a scenario when you have created a base model, then you're doing QAT first. So what we'll do is it will freeze the quantization range, and subsequent pruning and clustering will invalidate those calibration statistics. Like 0 point or scaling factor will get a problem when a QAT is done before pruning or clustering. That's why it's always preferred to ensure that pruning is done first, clustering next, and QAT, and later on at the end you're converting it to TF-lite to get the complete picture of. Okay. Okay. With the pruning, what you can expect as a gain? It's like the pruning could be between 50 to 90% depending on your base model architecture. Clustering 2 to 4x gain based on the k-mean value selected for centroid. And the QAT and PTQ is like up to 4x gain. You're converting FP32 weights to int8. So it's a 4x gain in that case. Moving next, it's a compression workflow. Okay. So what happens is, this is a full optimized journey. Each step shrinks the model further while maintaining the accuracy. You could see that the base model is 100%. When you're shrinking after pruning, it's going to be 50% or even less than that. After clustering, it will go further down. And then after QAT, from 25%, it goes to, let's say, 10%, even less than that. You could see the example also, where model could go down to 1% also from, let's say, base in megabyte to kilobytes, and without impacting the accuracy of the model. You could see that. Okay. Okay, next
All
poll.
right, so time for the next poll. And what we're curious to know is, when you're thinking about compressing the models from a very large size to a small size, what, in your opinion, would you consider a successful compression for you? Would you be happy with just a 25% reduction? Would you aim for more than 5 times reduction? What would be your criteria for success when it comes to model optimization? So we see that most people here are actually shooting for the stars. They're saying that they would be happy only with a 4x compression in model size and nothing less than that. And we see quite a mixed, humble lot over the other answers, where most people saying that 51 to 100% model compression would also work for them. So in your experience, Madanjit, what would
Yeah.
you say is the average compression in model size that is achievable on a more practical level?
Yeah, sure, sir. It's interesting spread. I could see that, and that's expected. The definition of success depends on your hardware and the use cases. Okay. For a drone, it might be a latency. For a wearable device, it might be a memory or power, right? In most of the edge AI applications or projects, the 5x to 10x reduction is a solid success. But when you come to microcontroller or ultra or what we call micro edge devices, then we often push to 50 to even 90% smaller models. The key is balancing compression and accuracy, but still achieving what is required for that use case. You can go up to even 100% also.
Okay, very interesting.
It's very interesting. Yeah, that's correct. So choosing the right optimization pipeline. Okay. You could see higher grade pipeline. You could see here is actually there's no single best optimization pipeline, as it depends on the use cases. Industrial systems may prioritize reliability and robustness, while the variable demands the smallest model footprint, right? So you can, however, follow certain guidelines based on the factors, like the type of input data you are feeding into the network, normalizing requirements. Either you can normalize the data which is coming in, or you can leave as it is. The complexity of features, Let's take an example that in the cases of sensor fusion or microphones, you are actually extracting the features out of it. In that case, you can prune heavily. But when you're taking camera, it's actually a raw feed. Very few cases we do the feature extraction for that. So it depends on what kind of complexity of feature you have and the depth of the model. You can take care of that. So there's no hard and fast or single based optimization pipeline. But what I experienced is when you have, in most of the cases, whenever you have the features of the model, it's better to start with the base, do the pruning, both the prunings, structured pruning and unstructured pruning, followed by the clustering and then quantization. That will give you the best result compared to anything. And based on use case, you can decide, I want to do clustering only, I don't want to do pruning. Or I don't want to do structured pruning, I want to do only unstructured pruning. That's possible. You'll get a good result. But end of the day, based on use case, you can balance it out, your optimization techniques. Okay, this is coming the final one where the trade-offs comes into picture. Like whenever you're developing something, you have to measure the performance. A smaller model might not be helpful if it becomes too inaccurate, because when you're quantizing a model will become small, but might be possible that it will become too inaccurate, too slow, or still exceeds memory limit, because micro SD devices are having 64 KB and 128 KB. But those who have worked on LLMs and all will actually be curious how to fit a model where the SRAM size or the RAM size, the memory size is 128 kilobyte, right? It's very interesting fact for that. What all things you have to map to measure to the to ensure that the model which you built is performing well as accuracy and F1 is standard. But for edge devices or micro devices, it comes like the model size, the latency, power, energy per inference, and memory footprint. These are the ones which comes for micro edge devices, not for cloud and all. For cloud, you have all those resources, whatever you need. So you have to look into that training. It's very interesting fact when you're working on micro edge devices or edge devices, you have to understand the network at the depth to do the customization of a model. That's a base model, and from there you can prune it and you can reduce the size to a level where you can deploy to even 64 KB model. Now 64 KB memory hardware. Okay. TensorFlow model optimization toolkit. In fact, what happens is TensorFlow and other AI model development frameworks like TensorFlow is there, Keras is there, which is actually underneath uses TensorFlow. Then PyTorch is there, Cafe, CNTK, all frameworks let you apply all these techniques what we discussed as a training wrapper, then fine tune at each level and then strip it for the inference. So that is possible in all those frameworks which are available. In session or in the demo which I have, I've done something on TensorFlow, which will give you a glimpse of how a base model is created and step by step and reducing without impacting the accuracy of the model. Okay. So we'll move to the live demo then. Let me open. Stop sharing.
And while we're getting the live demo set up, just so that everyone is aware, we'll be sharing the script, the code script that Madanjit will be walking over at the end of the webinar. So please stick around. Those will be unlocked at the end, and you'll be able to download the entire code script from the resources section. Any questions for anyone in the meantime? Please feel free to add any questions in the Q&A section, and we'll be very happy to answer them for you. Okay, there we go.
See that? Okay, it's fine. So optimizing AI model for edge and micro edge device. Why I'm using edge and micro edge both, because edge varies from, let's say, 512 KB to all the way to 8 MBs or 12 MBs of memory. Whereas micro edge comes into picture, it will be maximum, will go to 512. That's what I have seen. So micro edge devices are like small footprint memory devices where your model has to be in KBs, not in MBs. Okay. The strategy which we have used is I've created a large base model. Then structured pruning I have done, and unstructured pruning also I have done. High pruning is actually unstructured pruning. Then clustering I have done with 8. Lower precision, again, QAD I have done. And then the final stage is creating a TF-like model. Okay. You can see step by step, this is a modular approach I have taken where I've created around 11 steps to reach to the final numbers. So as we do as a data scientist, we generally, if we follow a complete structure, then you have to put a proper markdown for each and every block. It's a load library and warning suppressor. I don't like warning. That's why I've suppressed all the warnings. And warnings will always come when you are dealing with thousands and thousands of libraries which are built on different versions. So that's why warning suppression is always good to put in, because you don't know which version of TensorFlow or Keras or Panda or NumPy will start creating or colliding. So that's what I've done. So load libraries I have loaded, and then finally I've suppressed all the warnings. Helper functions I have put in, which will actually help us creating the metrics for each and every model created and then compare it, like get model size, get ggip size. Like ggip size will come into picture when it'll quantize a model, but still those 0 weights are holding memory positions. So when you'll do ggip, it will go down, the size will go down. Then sparsity will be there, count filters, and then reducing the filters based on the number of filters what you're trying to get in during your structured proving, counting parameters and get model summary and so on. Third step is like TF-like creation and evaluating of the model. Why I'm running this? Because this model creation of the complete cycle takes around 1.5 hours. So I cannot do live, but I have done it just before this webinar. This will be available for everyone to practice. You can just take it in your Jupyter notebook and you can run, you'll get the result. Here we are using a standard data set, because if you are a data science guy, the first data set we are going to experience is MNIST data set. Like it's like, it's an image data set with 60,000 training samples, all are annotated, and 10,000 testing samples for the digit recognition from 0 to 9. So 10 digit, 10 classes, and it's like, handwritten digits with the image size of 28 into 28 grayscale. This is very standard. So there's no need for you to have it locally. You can just load from Keras dataset and you'll get the dataset and you can work on it. Then I'm doing some changes into it, like, I'm ensuring that the input is standardized between 0 and 1. That's what the calculation. If you want to work on the full data set with the value of 8-bit, which between 0 to 255, we can continue with that as well. There's no problem. Okay, these are the standard. So that's the data set, and you could see the values. Once you go through this, you'll understand better, and maybe you can create your own model. So create base model. The first step is creating a base model, and base model from where you're getting. Everywhere it's available. You just go in Kaggle or anywhere, you can get structure. And based on your understanding, you can have this and create a base model. You could see after creating base model and training for 10 epochs, the model is created. Large base model of H5 is created, and you could see the parameters. These are 3.6 million parameters, which holds around 13.75 MB of space. Okay. After 10 epochs of training, you see the accuracy, training accuracy is 99.61, and validation accuracy on 10,000 on 6,000 data is 99.23, because I have taken 10% from training itself for validation. So accuracy you could see is 99.4%, which is very good. Raw image size coming as 40, sorry, raw size is coming as 42 MB, And G-chip size, again, some values will be zeros and so on and so forth. That's why 39 MB. The parameter size is 3.6. And then convolution filter, forget about it. But, once you'll understand, then you can play with it. The convolution filter, I've used 384 filters. Okay. Moving on to next, strategy 2, structured pruning. Now, if you understand the architecture, the one which you use for base model, you can prune it by changing it. So you can see that I have changed it by with a 90% or 80%. You can decide based on your use case. For this use case, I've used 90%. I've reduced it, and you could see same thing. I'm not doing anything else. Again, I'm training with the 15 epoch. And then second model is created as structured pruning model, which you could see here. The total parameters are just 50,000, close to 50,000, okay, 49,000. So from the size of 3.6 million, I'm bringing down to 50,000 by removing 3.5 million, 3.5 million parameters. And I could see I'm still getting accuracy of 98.63%, which is just 1% down from the bigger model, the base model. So that's what the power of quantization is, or pruning is. You can get it if you understand with bringing down the parameters from 3.6 million to just few thousand, and we're still getting 1% accuracy. So from 99% coming to 98.37%, which is still good. Okay. Forget about filters. You can count these filters. These are just for information purpose. And G-chip size, you could see, has gone down. Third is unstructured pruning. Then on top of that, I'm doing aggressive pruning of 80% sparsity. So what happens is I'll try to ensure that 80% of the weights are going to become zero. So I've done another check where I'm running 10 epoch, and you could see the change. After 4 epochs, it's realized that it can't go below that. So that's why, but still the accuracy is maintained as 98.51%, just 0.88% down from the original base model. The raw size has gone down to 220 KB, and G-chip size is 151 KB. The parameters will not go down because still the zeros values are still hold the memory locations. That's why parameters will still be there. But sparsity is 23%. When your compiler supports sparsity, your computation will go down with that. Okay. Fourth strategy is like clustering. Again, we discuss. So you have to define the K value for the clusters. So we have created 8 clusters, and you can see again I have done the tuning, fine tuning of using the 10 epochs on top of the pruned model, unstructured pruned model, and the output is after 10 epoch. You could see still it's 98.5%, and G-chip side you could see it's gone down to 27 KB now. It's smallest from 48 MB, it has gone down to 27 KB. Parameter will still be same because still those zero values are holding the memory location, and that's why it is. Okay. Fifth one, on top of that, after clustering, I'm doing the quantize aware training. Okay. So why quantize aware training is required? Because your weights are holding FP32 or floating point 32 value, a single precision float value. Then from there, you have to bring it down to int 8, which is 4 times or 4x performance or gain. Then for that, you have to train. And for training that, the model is already there. Okay. What you have to do is you have to give that input with the quantize aware training so that you'll set the parameters or statistics to ensure that the zero level and the scale are created based on the input values. So here you could see after 10 epoch, so the parameter has gone a bit up around 200, 300. Why? Because the zero factor and scale comes into picture. For further calculation will convert into TF-like model. Okay, but still accuracy is 98.73%. Could see the accuracy is maintaining above 98% every time. Doesn't matter how many stages or step-by-step quantization you do, end of the day, still after 5 phases or 5 stages, you're still at 98.73% accuracy. And then this is the last. To realize whatever you have done, you have to convert into int A. Otherwise, up to this point, your model will have floating point weights and biases to convert to actually realize that int 8 or each weight will be converted to int 8 from 0 to 255 or minus 128 to plus 127. You have to convert into TF light. And that's what the final stage is. And with that, you could see the compression ratio has gone to 749%. This is not true in all the cases, but in this case, it has gone down to 749%. And total reduction is 99.87%. And accuracy is still 98.73%. Okay.
So we have a
That,
question submitted in the chat.
yes, please.
Um, and we have Shubhojit Banerjee asking us if in this example, for each
Mhm.
optimization step, are you training from scratch or training on top of the model from the last step?
No, it's getting trained from the previous model. So if you're creating a base model is created. When you're doing pruning, structured pruning, if you're doing, then you're taking base as a model and doing structured pruning. From structured, you're doing unstructured pruning. It's like sequence, it's a pipeline. It's not that every time I'm taking base. If I take base, in that case, QAT to TF line will be only 75%, right? Whereas I could see 99.87%. It's a stage one with a pipeline from base model to all the way TF line. We are achieving 99.87%, which is quite high. Which is, you could see that, I know it's not ideal scenario, but in this case, we have achieved this accuracy. And most of the cases, 75% is very common. On top of that, you can achieve 10, 15% extra. It will always be there. Okay. And this
So,
is final number. Yeah, go ahead, please.
so I can see three participants have raised their hands in the chat. Please feel free to submit your queries as questions and we'll answer them for you.
So in this case, you could see the final achievement is 749% smaller. Size reduction is 99.87%. Parameter reduction is 98.64%. Accuracy maintained is 98.73%. Drop just 0.66% from base model, which was having 3.6 million parameters to a 49,000 parameters. The model is still performing at the same level. And hardware efficiency has increased because no, we have gone from floating point 32 to FP for FP32 to int 8. And then inference speed is, you can see that's 749% faster. But that's what, and this model is ready to be deployed on edge devices or micro edge devices. It'll give similar performance of what you can get with the base model in the cloud. Okay. So we'll take questions after that. So the final recap is like, now that we have covered the theory and model building, the live demo, we're open to have questions from you guys and we'll answer those questions. If anyone has questions, just put it in chat and we'll answer those questions.
So I can see a couple of questions coming in. I'll answer the first question from Shailesh Kulkarni. He's
Okay.
interested to know the most relevant industrial application for Edge AI. So if I can just share my screen for 1 second, I will
Yes, please.
talk about
Go
the
ahead.
so I think you should be able to see my screen now. And the answer for most relevant application for industrial edge AI is there are a couple of applications that we can think of, and there's certainly more. So the first one is predictive maintenance. And the idea here is that when you have very large machinery, very large pieces of equipment in a manufacturing or industrial setting, often those machines can fail unexpectedly, and that causes a lot of downtime. So if you can create a small module that sits on top of the machine and can measure the vibration, the sound, the electricity consumption, the power draw, and as soon as it detects any sort of an anomaly, it can alert the factory operator that, hey, look at the machine, let's do some quick quality checks before it breaks down. So predictive maintenance can be quite a useful application for Edge AI because instead of sending all the data to the cloud, if we can do the compute and the sensing right on the machine, it can be a lot more real time. It can be a lot more instant and also saves you a lot of compute infrastructure cost that is associated with setting up the cloud environment. Similarly, another application that we can think of is leakage and fault detection. So a lot of industrial settings will have gas pipelines or water pipelines, or even working with a lot of hazardous chemicals, hazardous gases. So if we can use AI compute with a combination of sensors to detect even the tiniest of leaks, which are not really easily caught by something as simple as just a pressure sensor or a flow sensor, then we can again save a lot of wastage and resources for factories and these kinds of industrial operators. And while there are many other applications that are relevant in industrial settings, these are some of the two common, most popular applications that we see. So I hope that answers the question for Shailesh. And then the next question from Ashish Goyal is, can you share performance improvements after optimization in terms of use case wise inference timing?
Yes, we'll do that. So right now, see, inference time for edge and micro device, a micro edge device always depends on the size of the parameter, the number of parameters you have. So if a parameter goes half, then definitely your performance is increasing 2 times. That's what it is. That's a ballpark you can use. There are any number of other factors also comes into picture, but this is the ballpark you can say, if my parameters, the base is, let's say 3 million, at the end, it's going to be 300,000, then 10% improvement is there. No, not 10%, sorry. It's like 1,000% improvement. Sorry. Yeah, 100%, sorry, it's a calculus. 100%.
All right. So I think since we're coming to a close on the timing here, we'll be announcing the lucky winner of the development kit. We'll be able to use that to develop various types of edge AI applications with our energy-aware AI processor. And these applications will span across Face ID to wearables, to smart rings, human activity recognition, fall detection, to keyword spotting, voice commands. There are many, many different edge AI applications that can be developed using our development kit. But before I get to announcing who that lucky winner is, as I promised, I am unlocking the presentation as well as the script that was used during our webinar. So now you'll be able to download it from the resources section. If you haven't looked at our link section, please visit our website, follow us on LinkedIn so that you're up to date with all the new promotions we're doing, the next webinar that we'll be doing. We're constantly posting a lot of useful educational content on semiconductors, on AI. So please be sure to follow us. And I'll now
One
announce our
more,
lucky winner.
one more fact check is also there. So as you can see that the last.
Yes, yes. Actually, there is one last poll, which I'll just leave open. People can feel free to answer that. And I'll now announce the lucky winner, which is selected at random from the chat right now. So the winner of the development kit is Rasagna V. Congratulations. You'll be hearing from us after the webinar. We have your contact details, so we'll reach out to you and we'll figure out how to get you the ambient development kit. So thank you everyone for attending the webinar. We're very glad that you showed up and made this a successful event for us. Once the webinar ends, all of you will be getting a survey to fill out where you can help us improve our next webinar and tell us whether you actually liked hearing from us, what was most useful for you, how we can improve it the next time. So I think that's it. With that, we'll be closing the webinar in a couple minutes. Any last questions? We'll just wait for a few more minutes to see if there are any last questions, and then we'll end the webinar. So someone is asking, will we provide software support to these boards? So our development kit comes with the software development kit as well. And that's actually a very, very full stack software development kit that enables you to do almost everything that we just walked over. So ranging from data collection to model training to model deployment, to all the standard middleware like your operating system, device driver. So it's a very end-to-end software development kit that you can use to develop and build your edge AI applications. And you can find the Jupyter Notebook code if you click on the resources at the bottom and hover over to documents, you'll see one of the documents that says ambient sample model compression. So you can download the file from there. So someone's asking, when we develop different projects, will you support? So the answer to that is yes, in the sense that once you have a development kit, we'll conduct an initial training with you where we will help you understand how to use our software development kit, how model training and deployment actually works on our hardware. And then when you have specific questions about the exact models or the exact use cases you're working on, we'll, of course, have our support team on standby where we'll help answer questions for you related to our hardware and how to deploy on it. Someone's asking, what's the general availability and obsolescence timeline like for the chip? So general, if by general availability you mean the lead time to purchase the development kit and the lead time to get the chips, we have distributors all over the world, including in India. So if you were interested in purchasing our development kit, you could reach out to us at info@ambientscientific.ai, and we'd be able to connect you with our distributors and help you get our development kit within 2 to 3 weeks, I believe. And the lead time for the chips would also be similar, is around 4 weeks or so. Obsolescence timeline for the chip would likely be around 4 to 5 years from now. Do you have ready solution for DMS? We do have ready solution for DMS actually. And if you reach out to us after the webinar, we're more than happy to talk to you and understand your requirements. I think that's it. We'll be ending the webinar now. So if anyone has any more detailed questions where you'd like to speak with us, understand more about our project, have any use cases that you would like to try and develop on our processor, please feel free to reach out to us at info@ambientscientific.ai. Follow us on LinkedIn, send us an email, reach out to us in whatever means possible, and we'll be sure to get back to you.
Thank you
Okay,
all for your
awesome. Thank you,
participation and
everyone.
great input throughout the session. Thank you.
Thank
Thanks.
you so much.
Thanks.